Greetings and welcome to the Chemistry 222 Final Exam Review. And this time we'll hopefully give you an opportunity to try out some of the many things that you've learned for the final exam, which should be coming up shortly. Now, the final exam itself will be over all of the chapters from Chemistry 222. But in this review, we're going to focus pretty much on chapters 12 and 21. So the kinetics and nuclear chemistry chapters. So I don't want you to think that there's not going to be the other material on there, but since this is probably the newest material for you, I'd like to spend a little extra time and make sure that this stuff is all good to go. So again, the lecture final will be over chapters 7 through 12, 20, and 21. So it'll be over things from Lewis structures to VSEPR, to valence bond theory versus molecular orbital theory, organic chemistry, gases, liquids, solids, transitions between them, solutions, and now most recently, kinetics and nuclear chemistry. If you are taking Chem 222 as an online class, then the final exam will have 32 multiple choice questions, and it's due by Friday at 9 a.m. via email to me, okay? And if you have questions on anything, let me know. I will be able to post your final grades by Sunday at noon at the latest, if all goes well. I do not return final exams to students, though, so I'm just letting you know. You'll be able to see your score, but I won't return the actual exam to you. If this is a regular face-to-face course, I'll talk about what the final exam will be like during the lecture. And regardless of whether you're taking Chem 222 as a totally online class or a face-to-face class or any combination thereof, if you do have questions, I want you to email me your questions, all right? Because the only dumb question is the one that's not asked. And I'm happy to help you. And I know that this can be kind of confusing sometimes, so I want to try and lower the confusion barrier as much as possible. Okay, I do wish you the best with your studying. And if you're ready, then we'll get into the review. And like the other online reviews of midterms that we've maybe seen already, this midterm is basically looks like a series of iClicker questions. I don't have a mechanism to offer you extra credit in this video, but on the other hand, you can still look at the question. I recommend pausing the video, and then you can work on the question, and when you're ready, unpause the video, and I'll talk about the answer in a few seconds. Okay, so without further ado, let's get into the questions. First question, for the reaction below, what is the change of CH2O over change in time with respect to delta O2 over delta time? And there's the equation right there. Now, this question goes along with how to describe the rates of reactants and products. And if you recall, there's a way to refer to the rate of any reactant and product. And basically what I want you to do is I want you to see what delta CH2 over O over delta T is with respect to the delta O2 over delta T. So see if you can figure out which of those is the right answer. I do recommend pausing the video. You can work on the question and then unpause it when you're ready. Pause the video now. I'm going to assume that you worked on the question and you're ready to tackle the answers. In the kinetics chapter, we talked about how the rate of any chemical can be used as a way to tell how fast or slow a reaction is. But there are two things you must do. First of all is that if it's a reactant, you have to put a negative sign in front of it. And the other thing is that if there is a stoichiometry, you go 1 over the stoichiometry to describe what's going on. So you can see in this problem that CH2O is a product and O2 is a product. So if we were going to write an overall reaction rate for this equation with just the two products, let's start off with that. You would first write rate equals, and these are both products, so it's positive. But you would go for the CH2O, you would go 1 over the stoichiometry, so 1/2, and then you write the really weird change in CH2O divided by change in time. So that would be the rate with respect to the CH2O. And again, notice that first of all, it is a product, so we just have a positive number in front of it. And also we went 1 over the stoichiometry, like 1 over 2, okay? Now, for the O2, we would do something similar. So first of all, it's a product, so don't have to, you put a negative sign. But then I want you to see how it would be initially 1 over 1/2. And 1 over 1/2 is the same, if you remember your math, as a factor of 2. So you'd write 2 times delta O2 divided by delta T. And this expression right here would be one way to talk about the speed of the reaction. And excuse me, this part right here would be an equally good way to talk about the speed of the reaction as well. And we talked about how sometimes it's easier to talk about CH2O than O2, but sometimes it's easier to probably talk about O2 versus CH2O. So it gives the chemist the choice as to which speed or rate they want to talk to. Now, if you look at the answers up there, A through E, they're all just the delta CH2O over delta T. There's no 1/2. So basically we want to isolate the delta CH2O over delta T. And we can do that by, I'll just cross this part out right here. We need to get rid of the 1/2, and we can do that by multiplying it by 2. But if we do that side by 2, we have to do this side by 2. So it's very weird, but we're going to multiply both sides by 2. So then you've got just the delta CH2 over delta T, which is what all the answers start with. And that's going to equal 2 times 2, or 4 times delta O2 over delta T. So this is one way that you can relate the rate of one product to the rate of the other product. And because there's a weird 2 and 1/2 ratio, it ends up being 4 times the O2 divided by delta T. That would be the same as the rate of CH2O appearing. Kind of a strange thing, but if you have this down, first of all, I applaud you, because figuring out the speeds of the reaction is really important. And second of all, I applaud you even more because you turned two relative rates basically on each other, and you solved for the relative rate of delta CH2O over delta T, and you saw that was equal to 4 times the delta O2 over delta T. If all of this problem has been gobbledygook, like it doesn't make sense, all right, and you don't have to raise your hand and tell me, but I just want to let you know that honestly, 99.9% of the time for problems like this, if you remember that reactants get a negative, products get a positive, and you go 1 over the stoichiometry, so like 1 over 2, stuff like that, honestly, you're going to be good to go on these. All right, that's literally as much as most of the time we'll get into. The reduction of nitrogen monoxide with hydrogen produces nitrogen and water, and there's the equation. And it says the reaction is second order in NO and third order overall. The rate law for this reaction is, and there's 5 possibilities. See if you can figure out which one of those rate laws would be correct using this information. I recommend you pause the video. You can then unpause it when you're ready to talk about the answer. Pause the video now. I'm going to assume you had time to work on it and you want to check out the answer, so let's do it. So the second order NO means that you're going to have a little superscript in the upper right corner next to the NO concentration. So A and B are not right because there's no little 2 right there by where I'm putting the little star. All right, so A and B aren't going to work. Both C and D have a 2, a superscript 2, a squared, if you will, for NO. E is totally off the wall and kind of whacked, honestly, so just ignore that one. But anyway, the answer will be C or D. So we know that because C and D both have second order NO. When you write that little superscript 2, that means second order. Now, it also says that it's third order overall. And if you remember from lecture, if you add up all of the orders of all the reactants, reactants and pieces in the rate law, that equals the overall rate order. As an example of that, it means that the rate order of NO is 2, so 2 plus X equals 3. And X is going to be the order with respect to H2, the other reactant. So if you look carefully at C, there's a second order NO, and there's like an invisible 1 right there by H2. Scientists don't usually write the little 1, but that's like an implied first order reactant. And 2 plus 1 would give you a third order overall reaction. Answer C is going to be the best answer here. So this reaction is second order in NO, it's first order in H2, and it's third order overall. Now, if you thought answer D was right, you were probably looking at the stoichiometry of 2 right there. And sometimes the stoichiometry is the same as the order of respect to reactants, but it's not all the time the case, as you can tell in this example. The reason for it is that if you have a multi-step mechanism, the slow step is reflected in the rate law. So if this reaction is second order NO and first order H2, in the slow step, that means you have 2 NOs and 1 H2 coming together to do something. And then because there is a stoichiometry of 2 for the H2, there's going to be a subsequent faster step where a second H2 is reacting with something. So here's the punchline, don't necessarily think that these stoichiometries are going to show up in the orders, all right? Answer C was the correct one here, and that wasn't 2 and 2, it was 2 and 1. So don't assume that stoichiometries are the same as the rate orders. Cool. This is the same reaction as last time. Reaction is second order NO and third order overall. So again, that means that NO is a second order reactant, and that also means that H2 is a first order reactant. Now, NO concentration is being increased by a factor of 5. What will happen to the rate? And the rate change will be one of those 5 answers right there. I recommend you try this problem. Pause the video. You can work on it. When you're ready, unpause it. We'll talk about the answer. Pause the video now. I'm going to assume that you've tried the problem and you want to talk about the answer, so let's do it. As a quick review from last time, if you have a second order reaction, that means your rate law is going to be rate equals K times NO squared, because NO is second order. And then like we saw in the last problem, if it's third order overall, that means that H2 is a first order reactant. So 2 plus 1 is 3. Now in this problem, you're increasing the NO by a factor of 5. And this is where the order with respect to the reactants becomes really important. You take the factor of 5 there and you raise it to the order of the chemical you're changing. So NO, you can see there, is a second order reactant. So if you literally increase the NO concentration by 5, the speed or rate will go up by 5 squared, or 25 times. Second order reactants just go crazy sometimes in terms of speed when you change them. And this would be an example of that. Now, if we would have changed the H2 concentration by a factor of 5, and H2 is a first order reactant, the change in this rate or speed would have been 5 to the first, or 5 times faster. And that's pretty impressive too, but it's not as impressive as a 25 factor increase in speed. If this would have been a zero order reactant, then 5 to the 0 would have been 1. There would have been no change in the rate for zero order reactants. So whatever the order is, you take the change of the concentration, raise it to the order. That's the answer. Good to go. Here's a reaction where A and B is coming together to make C. And in the table there, you can see you've got basically 3 experiments. Experiment number 1, experiment number 2, and experiment number 3. And you can probably see that what they're doing is they're changing one reactant concentration while leaving the other one alone. So if you look at 1 versus 2, the concentration of A is going from 0.10 to 0.20, while B stands just at 0.20. 0. So the far right column, the weird delta C over delta T, that's another way of saying the rate, all right? So delta C over delta T is the rate for this reaction. Anyway, I'd like you to use those values, and I'd like you to figure out which of the following 5 possibilities is the correct rate law for this reaction. So in this problem, you have to first of all figure out the orders with respect to A and B using the different data points. And then once you know that, you can actually go back and find the value of K. So you can see there's 2044, et cetera, et cetera. Those are all K values right there. Now, I must apologize, but answer E is not correct. I think AC/DC is pretty awesome, number 1, okay? But that's really not the answer here. Very embarrassing. Anyway, see if you can do this problem. Pause the video, unpause it when you want to talk about the answer. Pause the video now. I'm going to assume that you've worked on the problem and you want to check out the answer, so let's get into it. So on this problem, first thing you got to do is you got to figure out the rates of A and B, the rate orders. So rate equals K times A to the X and B to the Y. So first we're going to find little X and Y, the orders, and then once we have those, we can go back and pump it into one of the experiments above to find the value of K. Okay, so starting this off, what you want to do is look at the experiments up there and find a condition where one reactant changes and the other one doesn't. So as an example, to find the order with respect to A, the X value, notice if you go 1 to 2, A is being doubled, 0.1 to 0.2. On the other hand, 1 to 2 for B, B stays the same. So any effect in the rate, which is this column over here, the far right, any effect on the rate is going to be a reflection on A. B isn't doing anything, B's not changing, so it won't affect the rate. So if you look at the A values there, first of all, the difference between 40 and 80, 80 divided by 40, if you will, is 2, and 0.20 divided by 0.10 is also 2. So you can think about it that you have a rate increase of 2, and that equals the change in the A, which is also 2 to the X value. And X is, again, the order, in this case, with respect to A. Now, in Chem 222 and Chem 223, the little X values, or Y's and Z's, will be 0s, 1s, and 2s only. So 2 to the X equals 2. If X was 0, 2 to the 0 would be 1, and obviously 2 is not equal to 1, so X is not 0. If X was 2, 2 squared, that would be 4. Well, 2 is not equal to 4, so X here is not 2. So let's hope here that X is 1, and it is. 2 to the first power equals 2. 2 equals 2. So guess what? That means that your A is a first order reactant, okay? So we just found that A is a first order reactant because the change in the rate is equal to the change in the concentration of A, and that's pretty powerful. We've got to do the same thing for B. So for B, what I would do, let me change colors here. For B, I would look at number 3 versus number 1. So I'm using a different color here. Notice that A stays at 0.10, but B goes from 0.1 to 0.2, all right? So the concentration of B here is changing by 2, and that's going to be 2 to the Y, the little order with respect to that one. Now, the rate, though, goes from 40 to 40. So 40 divided by 40 is just 1. So notice here that the order with respect to B, where B changes, will be different than the order with respect to when A changes. 2 to the Y equals 1. The only way that that can work mathematically is if Y equals 0. So in this problem, we have above, we have X equals 1, and we have Y equals 0. So at this point, let's go back and rewrite this rate a little bit. Rate equals K times a to the first power and b to the 0 power. But anything to the 0 power is just 1. So really you can write this then as just rate equals k times a to the first, or rate equals k times a. And if you look through all of those options, the only one with a to the first power is this one right here. All right. Of course, AC/DC is just for fun. I apologize. Answer A has a B, so that disqualifies that. Answer C has a B. Answer B has an A to the second power, and we found it was the first power. So let's hope here that K equals 400. But how do you find K? Oh, excellent question. What you can do is go back to the expression here on the left-hand side I wrote in blue, and I'm going to use the values in experiment number 1. So the rate was 40 in the far left, in the far column. That equals K, which we don't know, times A, 0.10 to the first power, and I'm not even going to put b in because it's just to the 0 power. 40 divided by 0.1 is 400, so that means here the answer D is going to be right. So again, I'm sorry for writing over some of this, but hopefully you can see that first of all, the far right column was the rate. I then looked at 2 sets of data where one reactant changed and the other one didn't. We found that A was first order, B was 0 order. Rate has to equal K times A to the first power, which really limited it to D, but just to make sure, I put in number 1 data, and we found out that K, sure enough, is 400. You could use number 2 or number 3, and you should get the same answer there too. So it's not too bad, just a little bit of funky math, but nothing you can't do. Cool. This question says, for the reaction A going to B, the disappearance of A is found to be second order. Which of the following will produce a straight line graph? When it comes to orders, there's graphical techniques for finding out what the order of a reaction is. And one of those answers down there would be correct. See if you can find out which one it is. I recommend pausing the video. When you're ready to hear the answer, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm going to assume you've had time to check out the problem. In a second order graph, there's really only one answer here. The things you would plot would be 1 over the concentration versus time. That's answer D. Answer D is a second order test. Now, going up a little bit, C is a 0 order test, the concentration versus time. B is the most common one we're going to run into. That would be a first order test, natural log of concentration versus time. There are no log kinetics trials as far as I know, so that wouldn't make any sense. And even though it's second order, you wouldn't plot concentration squared versus time. You would again want to plot 1 over concentration time. So it's kind of a nice thing to know, because when you want to find the order of a reactant, this is a handy way to do it. Here's a reaction, A going to B again. In this problem, though, the disappearance of A is found to be first order. And someone did a linear regression analysis of some data, and they found this value, y equals negative 0.00106x plus or minus 3.91. And the question here is, what is the value of the rate constant K? And there's all those different answers. See if you can remember what I said about rate constants K. Only one of these would make sense. I recommend pausing the video now. You can unpause it when you want to hear the answer. Pause the video now. I'm assuming you've looked at the problem and you want to check out the answer, so let's do it. Rate constants K are a type of inverse time. And so time is like in seconds, K values would be inverse seconds, or if time was in years, K's would be inverse years. But because it's in time, and because this is chemistry, time, like matter, grams, is a number that always has to be positive, right? Maybe in physics you could get away with negative values, values, but certainly not in chemistry. In chemistry, time and the rate constants, which are related to time, have to be positive numbers. So of the answers there, you can probably see it's going to be either B or D. A and C are negative numbers. That's not going to fly. 42 is your instructor's poor attempt at a joke. It's a reference to the Hitchhiker's Guide to the Galaxy. If you know about it, cool. And if you don't worry about it. Again, my supreme geekdom here is showing through. But anyway, the question between B and D then comes from, is the positive value going to come from the slope, which is the negative 0.00106, or is the rate constant K going to come from the y-intercept of negative 3.91? And if you remember back from the notes and stuff we talked about, it's the slope that's going to give you the K. And because K has to be positive, let's make that negative a positive number, 0.00106. So in a first order graph, you would plot natural log of concentration versus time, and the slope will be negative. You'll have a negative slope. The slope is always related to the rate constant K, regardless of if it's second order, zero order, or first order. So if it is related, then it's either going to be used as is or make it positive. And in this case, we certainly want to make it positive. So 0.00106 is going to be the value for K. Now, the negative 3.91 number, that can be related back to the initial concentration of whatever it is you're talking about. And we talked about how you can take the natural log of A naught, the initial concentration, equals the y-intercept. So in this value, the initial concentration, 0.020 moles per liter. But that's not really important here. We just wanted to talk about rate constants, K. Remember, K is always going to be a positive number. Here's a reaction, A to B. Again, the disappearance of A is first order. Here's the rate constant, 0.030. That per minute is basically saying minutes minus 1, all right, inverse time. And we're beginning here with an A value of 0.36 moles per liter. What will be A after 46 minutes? I definitely recommend that you use the integrated first order rate law to solve this problem. Hint, hint, hint. I do recommend now that you pause the video, work on it. When you're ready, unpause it. We'll talk about the answer. Pause the video now. I'm going to assume that you've tried the problem and you want to check it out. So let's talk about how to get the answer. Again, on a problem like this, what I would recommend, I would use natural log R over R0 equals minus KT. All right, this is the so-called first order integrated rate law. R0 is how much you start with, R is how much you have left, K is the rate constant K, T is the time elapsed. So if you go through this stuff, K is 0.030, the T value, 46 minutes. And notice that K and T have the same kind of time, and that's important. You want to use inverse minutes and minutes. You wouldn't want to use inverse hours and seconds, something like that. Anyway, you're beginning, i.e. R0, with 0.36 molar, so the only thing then you don't know is R. So you can solve for it. If you look at all those values, answer E doesn't make any sense, because E is a number greater than how much we started with, 0.36. So that one's flat out, but the other ones are potential possibilities. So math to the rescue. Let's solve for A. Okay, I used A's here when I just wrote down R's. Sorry, this is my constant turmoil as an instructor. But anyway, we're solving for A or R, whichever one you want, doesn't matter. Anyway, first of all, you want to get minus KT. Then you want to use the inverse natural log. So you'd go, for example, you would go e to the negative 1.38. That's how you'd go from negative 1.38 to this number right there. That's getting rid of the natural log. You use the anti-natural log. It's usually second function ln on your calculator. Anyway, A over 0.36 equals that number. So A equals 0.36 times that number, 0.091 moles per liter. So again, very useful equation, and almost everything is first order in science. Not everything, but a lot of things. I recommend getting used to that equation. Here's a problem with radioactive gold 198. Most gold is not radioactive, but this one is. Apparently it's used to look at liver problems. Pretty cool. Anyway, the half-life for this isotope, 2.7 days. We're beginning with 5.6 milligrams of the isotope, and we want to know how long, how many days it takes to take 5.6 milligrams of gold to 0.70 milligrams of the gold. So this is another kind of problem. Radioactive things, like all biology things, are always first order. So you can use natural log R over R0 equals minus KT. However, there's no K value here. So you have to somehow think about how half-life relates to K. One of those answers will be the right one. I recommend pausing the video. You can work on it, and when you're ready, just unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've worked on the problem. You want to check out the answer. Let's do this. So let's go back. Natural log R over R0 equals minus KT. And sometimes I use natural log A over A0. You've already seen it. So if I do that again, I apologize. It doesn't really matter. R0, how much you start with. R is how much left at time T. So in this problem, 5.6 milligrams is R0. That's how much we're starting with. And we want to know how long time T it's going to take to get to 0.70 milligrams. So 0.7 milligrams is R. We want to solve for T, but we don't know K, all right? However, we do know that the half-life of the isotope is 2.7 days. Along with the integrated rate order expression, I also recommend remembering that half-life, T1 half, 0.693 divided by K. So if you have half-life, you can easily find the rate constant K. And if you have K, you can find the half-life for that matter. That's how that equation is what we're going to use to solve for the rate constant K. And then we can plug it in with our gold values to find the time elapsed. So in this problem, oh, here we go. See, I use natural log A over A0 instead of natural log R over R0. Sorry, spastic instructors. Anyway, here's the important part. Natural log A over A0. So A0, how much we started with, 5.6 milligrams. A is how much is left, 0.70 at this weird time T. But we didn't have K, we didn't have T. However, here is the way to solve for K. 0.693 divided by the half-life, divided by 2.7 days. So when you solve for T, you end up coming out with 8.1 days. I didn't even solve explicitly for K. I just threw it all in the equation stuff. You can do it either way. K would come out to be inverse days because the half-life was in days and the final time is in days. No problem. They're all the same kinds of units. Life is good. It's really cool to know, yeah, A and A0, or R and R0, have to be the same kind of unit, just like T and K have to be the same kind of time unit. Of course, K would be inverse time instead of regular time. Oh, joy. The reaction of NO2 and carbon monoxide is thought to occur in 2 steps, and you can see step 1, step 2. Also notice the slow and fast. So the question says, which of the following rate laws would correspond to this mechanism? And there's 3 possibilities. I'd like you to make your best shot. If you wish to pause the video, you can think about it a little bit, figure out the right answer, and when you're ready, unpause the video. I'll talk about the right answer. Pause the video now. Okay, I'm going to assume you've worked on the problem. You're ready to talk about the answer, so let's do it. Rate laws and slow mechanism steps go together, and that's super important. So this slow step, the reactants are going to appear in the rate law. And you can see in the slow step, there's not just one NO2, there's 2 NO2s. So the slow step of this transformation says that 2 NO2s are coming together to make the weird NO and NO3. We don't really care about that in this problem. In the slow step, the reactants were 2 NO2s. So you could think about the slow step, you could write it as rate equals K times NO2 times a second NO2, or what of course everybody does, rate equals K times NO2 squared. NO2 is a second order reactant here. If you figure out the overall reaction, I believe it's just NO2 and CO making CO2 and NO. It's 1-to-1 NO2 to CO stoichiometry. But in the slow step, two NO2s must come together to make that really wild NO3 intermediate. That goes on to react with CO in a fast step to make those other products. So in this problem, we would consider CO a zero-order reactant. It's not part of the slow step. And NO2, because the slow step has two of them, NO2 would be a second-order step. Overall rate order would be 2. Cool. Use the rate laws below to determine which reaction is most likely to occur in a single step. So look at the 4 reactions there with their 4 rate laws, and one of them we would expect to occur in a single step. See if you can figure out which one it is. If you need to stop it, pause the video, you can think about it, and when you're ready, you have an answer, you can unpause it, and I'll talk about what the actual answer is. So pause the video now. I'm going to assume that you've had a chance to work on this and you want to talk about the answer, so let's get into it. In the last problem, I said how the slow step reflects the reactants, all right? So in the last problem, it was a 2-step mechanism, and in the slow step, there were 2 NO2s coming together, so rate equaled K times NO2 squared, i.e. the slow step reactants end up in the rate law. So on this problem, if it's a single step, all of the reactants will be reflected in the right ratios in the rate law. What I mean by this, answer A. Answer A, in the reactant side, we have 2 NO2s and 1 F2. If this was a single step, you would have rate equals K, you'd have an NO2 and an F2, but you'd have a 2 for the NO2. All right, and we only have a 1 for the NO2. So what that means to us is that in the slow step of this reaction, 1 NO2 and 1 F2 are coming together to do something, and then in a subsequent step, that something reacts with the other NO2 to make the products. But the important part here is that because we don't have 2 for NO2, this is not going to be the answer. This is not going to occur in a single step. The second one, H2 and Br2 making 2 HBr, notice how in the rate law, you do have 1 H2, and that's good because we have 1 H2 on the reactant side, but we only have half of a Br2. And if this was actually a single step, you wouldn't have half of a Br2, you'd have a full Br2 because 1 Br2 reacts with 1 H2. Answer B is also not correct. The stoichiometries of the reactants do not match the orders in the rate law, and that's kind of what we're after. However, if you look at the next one, you've got 1 NO and 1 O2 making stuff, all right? And in the rate law, you have a first order NO and a first order O2. 1 NO and 1 O2 would have a rate K equals 1 NO and 1 O2. Answer C is it, all right? So the stoichiometry of the reactants equaled the order of the reactants in the rate law, and that's what you look for if it's a single step. You can see in answer D, you don't have that either. You have just rate equals K times NO2. There's no mention of CO. CO must be involved in a subsequent fast step. So that's a cool way to see if you have a single elementary step, like one stop reactants going to products. And there are some reactions like that, but there's also a lot of them that are multiple steps. And so of these 4 reactions, we would say only C is likely to occur in a single step. A, B, and D probably have multiple steps going on to make those reactants turn into products. Which statement is incorrect? And there's 5 different statements there. I'd like you to try and figure this one out, all right? Pause the video, read through it, think about it, and when you're ready, unpause it. I'll talk about the answer. Pause the video now. I'm assuming you've worked on the problem and you want to talk about the answer, so let's do it. First of all, it might be tempting to think that E is incorrect. Catalysts are cool, all right? And yes, I'm a chemist, so I may be a little bit biased, but here's why I think that E is a correct statement. A lot of the things going on in your body right now are catalytic. They're all the enzymes that the biologists talk about, sugar making new products and all kinds of other things, all right? Those are all catalysts. So without catalysts, you'd be dead. So I think that catalysts are cool, all right? Answer E is not the answer here. Okay, so sorry to blow your bubble. It looks kind of cheesy, but I do want you to see catalysts are pretty important. In addition to everything in your body, catalysts help make a lot of the products we use in our day-to-day life and stuff. So anyway, so let's go through these one by one. A catalyst provides an alternative mechanism for a reaction. True. Catalysts do change how reactants go to products. We talked about in lecture how a catalyst makes extra humps usually, like at least there's 2 humps at least when a catalyst is involved. So you definitely have a different mechanism. You're lowering the energy of activation, making it faster to get from reactants to products. B, a catalyst is regenerated in a reaction. True. Catalysts should, at the end of the reaction, come back and ready to transform more molecules. All catalysts have a certain number of transitions they undergo, and people in industry will sometimes figure this out. But the numbers are usually in the million plus transformations. So what that means is that catalysts can undergo like 1 million transformations before they basically wear out. All right. So yeah, catalysts should be regenerated in a reaction. C, a reaction involving a catalyst yields more product. No, I don't think so. A catalyst will make the reaction faster, but it doesn't make more product. So the answer here, which is incorrect, is C. So let's reflect here a little bit on what it means to have a catalyst. So reactions which are slow can be sped up with a catalyst, all right? It makes the reaction go faster. You don't have to wait as long. But I wouldn't say that it makes more product, all right? You can change the pathway, maybe change the orders of reactions or something like that to make more product, but it doesn't make more product unto itself. Now D, a catalyst speeds up the forward and reverse reactions. True. By lowering the energy of activation barrier, it actually works in both directions. One direction is almost always higher than the other. So we're assuming that reactants going to products would be exothermic. The forward reaction would be lowered and the reverse reaction, but the forward reaction should be a lot easier to do than the reverse reaction, but they are both lowered. So catalysts pretty important both in our body and in the world and stuff. And if you secretly hate catalysts, I wouldn't hold it against you, but I'd like you to hopefully have a little bit of respect for these chemicals. They're pretty cool. How many neutrons and protons are there in the radioisotope 60 cobalt, which is cobalt 60? And cobalt 60 is used in cancer therapy. Okay, one of these answers is correct. I'd like you to try and figure out which one it is. You can pause the video, unpause it when you want to talk about the actual answer. Pause the video now. Okay, I'm going to assume you've worked on it. You want to check out the question. I'm all over it. You will need a periodic table for this question. I do recommend the one at mhchem.org/per-tab. It's the one in the companion, or you can use any one you want, really, but that's the one I like. But anyway, you need it to know, look up cobalt. Cobalt on the periodic table is number 27. And 27, the number on the periodic table, tells you the number of protons. So in this problem, cobalt 60 there is going to have 27 protons. If you change the number of protons, you change the element. So for example, if you added an extra proton, it wouldn't be cobalt anymore. You'd have nickel, number 28, etc., etc. So this answer has to have 27 protons. Now the little 60 there in the upper left-hand corner, that's the mass number. That equals protons plus neutrons. So to figure out out the number of neutrons, 60 minus 27, and again, 27 came from the periodic table. It's not magical or anything. That equals 33, and that's the number of neutrons. So again, protons from the periodic table, the atomic number. Neutrons equals mass number minus atomic number, 60 minus 27. Protons plus neutrons minus protons. All right, good to go. Pretty chill. This is kind of a review from Chem 221, but it's really important because we're going to talk about balancing the nuclear reactions, all that kind of stuff. Speaking of balancing nuclear reactions, this transformation is missing a particle, i.e. what is the identity of the missing particle? And you can use your understanding of how to balance these nuclear reactions and figure out which one of those the answer is. I encourage you to pause the video, think about it. When you're ready to talk about it, you can unpause the video, we'll talk about the answer. Pause the video now. I'm going to assume that you've worked on the problem and you want to talk about it. Pretty chill. All right. These balancing of nuclear reactions are pretty mellow. The number of protons, the lower left-hand numbers, the atomic numbers, must equal the same number on both the left and the right side. And the upper left numbers, which are mass numbers, protons plus neutrons, the mass numbers must be the same on both sides as well. So unknown particle here, it has an unknown atomic number, which usually gets the symbol Z. It has an unknown mass number, which I'll put as A, and there's going to be some kind of symbol for it, X. Okay, so to find out what A is, that's the easiest. We take 239, the only upper left-hand number on the left side. 239 equals A, our unknown, plus 239. What? Anyway, 239 equals A plus 239. A must be 0. So the value for A in this unknown particle is just 0. Now in the lower left-hand corner, same game. 92 on the left equals Z plus 93. Z has to be a number, so you put negative 93 on the other side. Z here, negative 1. And if you remember from the notes from the nuclear chemistry chapter, something with a 0 on the top and a -1 on the bottom, it gets the symbol either beta or electron is fine. And beta means that the missing particle is a beta particle. So 0 minus 1 is a beta. And you can write it 0 minus 1 beta or 0 minus 1 E. Either way is fine. So this problem, this uranium-239, is undergoing essentially beta emission. Emission means that it's being given off, and that missing piece here is a beta particle. Here's a problem very similar to the last one. We have an unknown particle in this polonium decomposing into a bismuth. Figure out what the missing particle is. Pause the video, work on it a little bit. When you're ready to hear the answer, unpause it. Pause the video now. Okay, I'm going to assume you've worked on it. You want to check out the answer, so let's do it. So again, that missing particle is going to have some kind of weird atomic number Z. It'll have some kind of mass number A, and there will be some kind of symbol X that goes along with it. So let's do Z first. 84, the lower left number of polonium, equals Z plus 83. Okay, so in this problem, Z must be 1. Let's do the mass number now. 207 equals A plus 207. A can only be a 0. Okay, this looks a little strange at first because 0 plus 1. Lower left-hand number is usually number of protons, and upper left-hand number, protons plus neutrons. So if this was a proton, you'd have a 1 up there where there's a 0, but obviously this is not. So if you look back in your notes, believe it or not, this one gets a beta 2, but it's not an electron. This is an anti-electron, also known as a positron. Positron emissions do occur sometimes with certain types of elements. So 0 minus 1 beta was an electron. 0 plus 1 beta is a positron, an anti-electron. And when two anti-particles come together of opposite, then they annihilate each other. Lots of energy is released. This is kind of a cool thing. It's kind of like Star Trek, although not quite as cool, obviously. Or is it? I don't know. Anyway, Prof hat back on. A new nucleus is being produced in this nuclear reaction. They're taking a calcium-41 and they're adding a beta particle to it, an electron, and something new is being made. So figure out what that missing particle is. Pause the video. When you're ready to hear the answer, you can unpause it. Pause the video now. I'm assuming you're ready to talk about the answer, so let's do it. So this is like the last ones we did, only now the missing piece, the missing unknown particle, if you will, is going to be on the product side. So what I'm going to do is I'm just going to draw another ZAX kind of thing. Z is the atomic number, A is the mass number, and X will be the symbol. So on this problem, it's like reactants equal products as always. So 20 minus 1 equals Z. 20 minus 1 is 19. That means that Z here is going to be 19. On the top part, same kind of thing. 41 plus 0 equals A. So 41 equals A. We would write 41 right there. And if you look at those different symbols, the only one that follows it is going to be C. Anything with 19 protons in the lower left corner, look on the periodic table, that's going to be potassium. So this would be a potassium 41 isotope that has been created. Again, just same thing, lower left-hand numbers must on the reactant side must equal lower left-hand numbers on the product side, and the same thing for the mass numbers. The upper left-hand numbers on the reactant side must equal the upper left-hand numbers on the product side. You just kind of let them equal to each other, see what's happening, good to go. Here are a series of elements, and I'd like you to tell me which one has the highest binding energy per nucleon. Now, you could look up the values on Google and compare that, but there's an easier way. So by hook or by crook, figure this out. Pause the video. When you're ready to hear the answer, you can unpause it. Pause the video now. Okay, I'm assuming that you've looked at the problem, you want to check out the answer, so let's get into it. This question has to do with thermodynamic stability of the different isotopes, and we use the binding energy to figure out which ones were more stable. And if you remember the discussion from lecture, the most stable isotope of all the thermodynamics, is iron 56. So iron, which is number 26 on the periodic table, iron 56, that isotope specifically, is the most stable, and things that get to iron 56 basically stay there. So if you have a series of elements like this, what I would do is find the element closest to iron, closest on the periodic table to iron, and absolutely nickel is the closest one. So I would guess off the top of my head that the nickel 59 here is the best answer. I don't believe you, Dr. Russell. Okay, whoever said that, let me give you the actual values. And yes, I do use Google as well. There's no shame in that, that's for sure. I looked up the actual binding energies per nucleon. These binding energies are in what's called a mega electron volt. A mega electron volt is just equal to a lot of joules. You can see there. So you can translate these all into joules. So the bigger MeV number will be the biggest binding energy, and you can definitely see nickel 59 here dominates, 8.69 versus the other ones. So again, if you have to guess the one that's closest to iron. Iron on this little graph is right there. It's the top part of the binding energy curve. And you can see as you go to the right, it kind of gets a little smaller. Definitely going to the left, it gets smaller yet. But if you have to guess, i.e. if you don't have access to the internet / Google, then pick the element closest to iron. You'll be good to go. The fifth choice was a JQ. That's another dumb joke by your instructor. There are no permanent elements with the letters J or Q. All right. So one day I always hope that there'll be a new element with the symbol of JQ or QJ, something like that, because, we don't have Q's and J's on the periodic table. But anyway, it's another ridiculous joke. My apologies. Here's a question where I want you to calculate the binding energy per mole of nucleons for carbon-12, okay? This is the kind of question we did in the lecture notes. It's not too bad. What you want to do in this problem is you want to start with 6 raw protons and 6 raw neutrons. Those will be your reactants, and that's going to make carbon-12. Carbon-12 is going to be your only product. So on this problem, you first want to find the delta mass, delta M. Delta M times the speed of light equals the delta E, and go on from there. Remember, a nucleon can be a proton or a neutron. So you, at the very end, when you get the energy per mole, you want to divide by the total number of protons and neutrons in carbon-12. This is definitely a math-heavy problem, and I absolutely recommend that you pause the video, all right, and work on it a little bit. Just do as much as you can. You get stuck, no problem, all right, but trying it would be really good. You can look back in the old notes if you'd like to, but this is a process we'll use once in a while, and it is kind of cool because it allows you to find those binding energies, which isotopes are more stable, stuff like that. Okay, so pause your video now, work on the problem, and again, when you're ready, unpause it. We'll talk about the answer. Pause your video now. Okay, I'm assuming that you've worked on the problem. You want to check out the answer. Let's do it. But before we do that, let's look at some of the answers real fast. Answer D is a negative number, and all binding energies are positive. They represent the strong force, how much it contributes to stabilizing the nucleus. If it was a negative amount, then it would be an unstable nucleus. That just doesn't sound right. Answer E also is horrible scientific notation, and your instructor is really big into proper scientific notation, so D and E are probably not going to be the answers. But A, B, and C are all totally legit, so for this part, you kind of got to go through the math. Now, what we're doing in this problem is you're taking 6 protons and 6 neutrons, and you're making a carbon-12. So your reactants are the 6 protons and 6 neutrons, and you're making the carbon-12. And you'll take the mass of carbon-12 and subtract the 6 protons and 6 neutrons, and that will lead to a change in mass. And it'll be a slight negative number. The mass is being lost, all right, which is wild. Now, to figure out the energy, you need to take the mass, turn it from grams to mole into kilograms per mole, and then multiply by the speed of light squared. And that's going to give you the change in energy. And it'll initially be in something like joules per mole, and it'll be a big negative number. You can take the opposite of the delta E to find the binding energy. And finally, you need to divide binding energy by 12, because here we want the binding energy per mole of nucleons. Carbon-12 has 12 nucleons. 6 protons plus 6 neutrons is 12. So all of these things, you will end up with a positive number. There will also be a joules to kilojoules conversion in there. Okay, so that being said, let's check out the math. First of all, the answer is A. Okay, it's 7.411 times 10 to the 8th. So here's the change in mass, the delta M. It's the carbon-12 number minus the 6 protons minus the 6 neutrons. You get a negative mass. Mass has been lost, making carbon-12. And I talked about how that freaks chemists out because law of conservation of mass, blah, blah, blah. But anyway, you can turn this mass change into an energy. You do have to change grams per mole to kilograms per mole. So you can see there's an extra 10 to the negative third. That's the joules to kilojoules conversion. Then you multiply by the speed of light squared. And also on here, I turn joules into kilojoules. If you do all that, you get the negative 8.893 times 10 to the 9th. That's the delta E, the energy released upon making carbon-12. And again, that's kind of an important number because atoms have to have a reason to be made. The protons and neutrons have to have a reason to coming together to make atoms, all right? And that energy release is like a payment, all right? So like in the business world, when you make money, woohoo! Well, this is the chemist's way of saying woohoo, because you're getting a lot of energy out, all right? That's what that kind of thing means. But finally, binding energy is the opposite of the delta E divided by the number of nucleons. So if you divide that number by 12 and make it negative, 7.411 times 10 to the 8th kilojoules per mole of nucleons. So if you look at that chart on the last problem then, carbon-12 is probably on there somewhere, quite a bit of energy released per mole of nucleons. So it's a pretty good investment, if you will, of energy. You get a lot of energy out. The physical sciences are all happy. Oh, joy. Radioactive iodine 131 is used to treat hyperthyroidism. It has a half-life of 8.04 days. Let's say we begin with 8.8 micrograms. What mass remains after 32.3 days? All right, so this is a problem with radioactive isotopes. This is similar to the stuff we did in the kinetics chapter earlier. I would use the integrated first order rate law to do this problem. See if you can do it. All right, pause the video. When you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm assuming that you've worked on it. We can answer it, so let's check it out. So again, first order rate law, natural log R over R0 equals minus KT. I might use A over A0. That's kind of my way. But anyway, in this problem, it has a half-life. We're starting with 8.8 micrograms. So that's the R0 value. We want to know R, how much is left after a time of 32.3 days. So we're trying to find R, how much is left, but we don't have K. But like we saw in an earlier problem, half-life, T1 half, 0.693 divided by K. So if we take that half-life, put it in that expression, that's going to give K, all right? K will be in inverse days. That's good because we have a time in days, all right? Our R0, how much we started with, was 8.8 micrograms. So our R, how much is left, will also be micrograms. And if you do this problem, it comes out to be 0.54 micrograms. So again, I used A's instead of R's again. My apologies. We started with 8.8 micrograms. That's a symbol for micro. That equals minus KT. T is 32.3 days. K we can find 0.693 divided by the half-life. And you go through and solve it. Remember that to get rid of the natural log, you go e to the x. So e to the negative 2.7841 comes out to be this number, 0.061785, and the natural log on the other side goes away. So from there you can get 0.54 micrograms. Cool for school. Gallium citrate has radioactive gallium-67. It's used for tumor-seeking agents. It has a half-life of 78.2 hours. How long will it take for a sample of gallium citrate to decay to 15% of its original activity? And one of these answers here will be correct. See if you can figure out which one of those it's going to be. I recommend pausing the video. You can unpause it when you're ready to talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to work on the problem. Let's check out the answer. This is another problem where we're going to use that, yes, I know, you've heard it so many times now, integrated first order rate law. Natural log, let me use A's this time. A over A0 equals minus KT, okay? And A over A0, which is the same as R over R0, A0 how much you started with, and A is how much is left. But the thing is that's a ratio, okay? And ratios this can be used in lots of different ways. Now, we've seen it as molarity over molarity. The last problem, I believe, was micrograms after micrograms. In this problem, we can actually use percent activity because we're going to assume that A0 was 100%, and we want to know how long it takes to get to 15%. So we're going to use 15 on the top for A and 100 as A0. We started with 100%. Now, if you look through the rest of this stuff, we have a half-life. Half-life equals 0.693 divided by K. So that'll allow us to find the rate constant K. And then the only thing we don't have will be time, the time. And because half-life is in hours, the time elapsed will be in hours. So throw all that stuff into the equation. You can see there's the natural log 15 over 100 equals minus 0.693 divided by half-life. That's K, whatever it is. And then T is the only thing we don't know. So you solve for T. It comes out to be answer C, 214 hours. That ratio is really cool. You can use moles over moles, grams over grams, a percentage over percentage, decompositions per second over decompositions per second. As long as they're the same kind of units, you're good to go. That's the end of this review. I hope it was helpful for you. If you need more practice, I definitely encourage you to check out the practice problem sets, which are online and in the companion. They have some more problems and the answers are given at the end. There's also concept guides that have worked problems that go through the different things. Those are on the companion and online. Chapter guides are online lists of all the digital things that might help you study the material. And also at the end of your textbook, every other problem, the answer is in the back of the book. So you can do the ones with the answers, make sure you're on target, you should be good to go. I do wish you the best with your studying. If you have any questions, definitely feel free to email me anytime. Happy to help. You can also talk to the Learning Success Center /Avid Center. They will help you out as well. Okay, good luck with your studying and have a wonderful day.